In September 2024, astronomers made an extraordinary discovery that would send ripples through the scientific community. Using the ATLAS telescope system in Hawaii, they detected something that didn't belong to our solar system, an object traveling through space at speeds that could only mean one thing. It came from the stars beyond our sun. This wasn't just another asteroid or comet. This was 3IATLAS, only the third confirmed interstellar object ever detected passing through our cosmic neighborhood. And unlike the mysterious Oumuamua that came before it, this visitor from another star system would give us an unprecedented opportunity to study an alien world up close. Today, we're going to explore everything we know about this remarkable object. We'll dive into how it was discovered, what makes it so unique, what it tells us about other star systems, and why its arrival might be one of the most important astronomical events of the decade. So buckle up, because we're about to take a journey across the vast emptiness of interstellar space. To understand an object that traveled for potentially millions of years just to pass through our little corner of the galaxy. The discovery. Our story begins with the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short. This is a network of telescopes specifically designed to scan the night sky for potentially hazardous near-Earth objects. Night after night, ATLAS photographs the same patches of sky, looking for anything that moves, anything that's new, anything that doesn't belong. On September the 16th, 2024, ATLAS detected exactly that, a faint point of light moving against the background stars. At first glance, it might have seemed like just another space rock, another entry in the endless catalogue of solar system debris. But something was off. The trajectory was wrong. The velocity was wrong. Everything about this object's motion suggested it wasn't gravitationally bound to our sun. Within hours, other observatories around the world were alerted. Telescopes swiveled to confirm the sighting. Astronomers began calculating orbital parameters, running the numbers over and over, checking their work. Because if their initial calculations were correct, they were looking at something extraordinary. The data was undeniable. This object was moving at approximately 40 kilometers per second relative to the Sun, far too fast to be trapped in a solar orbit. Its trajectory showed it was on a hyperbolic path, meaning it would sail through the inner solar system and then escape back into interstellar space, never to return. The astronomical community quickly mobilized. After verification from multiple observatories and confirmation of its interstellar origin, the object received its official designation, 3I/ATLAS. The 3I indicated it was the third confirmed interstellar object, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The ATLAS credited the telescope system that first spotted it. But this was more than just a catalogue entry. This was a messenger from another star system, and astronomers had just won the cosmic lottery, the chance to study an alien world passing through our backyard. What makes it interstellar? You might be wondering, how can astronomers be so certain that 3I/ATLAS actually comes from interstellar space? After all, our solar system is full of comets and asteroids on highly elliptical orbits. What makes this object so special? The answer lies in orbital mechanics and something called orbital eccentricity. In our solar system, objects bound by the Sun's gravity follow elliptical orbits with an eccentricity between 0 and 1. A perfect circle has an eccentricity of 0, while increasingly elongated ellipses approach but never reach an eccentricity of 1. Even the most extreme long-period comets from the Oort cloud, taking millions of years to complete a single orbit, still have eccentricities just below 1. But 3I/ATLAS, its orbital eccentricity is greater than 1, significantly greater. This means its trajectory isn't an ellipse at all, it's a hyperbola. And a hyperbolic trajectory means the object has more than enough velocity to escape the sun's gravitational influence entirely. Think of it like throwing a ball upward from Earth's surface. If you throw it too slowly, it falls back down. That's like an elliptical orbit. But if you could throw it fast enough to exceed Earth's escape velocity, it would leave our planet forever, following a hyperbolic path into space. That's exactly what 3I/ATLAS is doing with respect to the Sun. The math is unambiguous. This object entered our solar system with excess velocity, meaning it was already moving through space before encountering the Sun's gravity. It came from somewhere else, another star system, another part of the galaxy. By tracking its trajectory backward through time and space, astronomers can even estimate where it came from. The calculations suggest 3I/ATLAS originated from somewhere in the direction of the constellation Ursa Major, though pinpointing an exact star of origin is nearly impossible given the vast timescales involved. This object could have been wandering through interstellar space for millions or even billions of years before happening upon our solar system. Physical characteristics. So what does 3I/ATLAS actually look like? What is this interstellar wanderer made of? Based on observations from multiple telescopes, including ground-based instruments and space-based observatories, we've learned quite a bit about its physical properties, though many mysteries remain. First, let's talk about size. 3I/ATLAS is estimated to be several hundred meters across, somewhere between 200 and 400 meters in diameter, though exact measurements are difficult given its distance and faintness. To put that in perspective, that's about the length of 3 to 6 football fields, large enough to be significant, but small enough that it remained undetected until it ventured into the inner solar system. The object displays a distinct coma, a fuzzy atmosphere of gas and dust surrounding a central nucleus. This immediately tells us something important. 3I/ATLAS is behaving like a comet. As it approaches the Sun and heats up, volatile materials on its surface, probably water ice, carbon monoxide, carbon dioxide, and other frozen gases, are sublimating, turning directly from solid to gas and creating this characteristic cloud. Spectroscopic analysis of the coma has revealed its chemical composition. The predominant gases detected include water vapor, carbon monoxide, and cyanogen, a carbon-nitrogen compound. These are typical cometary volatiles, similar to what we see in comets native to our own solar system. This suggests that comet formation processes might be fairly universal, at least among planetary systems in our galactic neighborhood. The color of 3I/ATLAS has also been measured. It appears slightly reddish, which is common for objects that have spent eons being bombarded by cosmic rays in interstellar space. This radiation slowly alters the chemistry of surface material, creating complex organic compounds that tend to darken and redden over time. One of the most intriguing aspects is the object's activity level. As 3I/ATLAS approached perihelion, its closest point to the Sun, its brightness increased significantly, as more material sublimated from its surface. Astronomers have been carefully monitoring this activity, looking for outbursts, jets, or fragmentation events. Understanding how an interstellar comet responds to solar heating compared to solar system comets can teach us about differences in composition and structural integrity. The rotation period has been estimated through careful observation of brightness variations. 3IATLAS appears to rotate once every several hours, though the exact period is still being refined. The way its brightness fluctuates can tell us about its shape, whether it's spherical, elongated, or irregularly shaped like most cometary nuclei. The journey through our solar system. Let's trace the path of 3I/ATLAS through our solar system and understand the timeline of this cosmic visit. The object's trajectory brought it into the inner solar system at a relatively steep angle to the plane where most planets orbit. It first crossed the orbit of Neptune in early 2024, though it was far too faint to detect at that distance. As it continued sunward, passing through the realm of the outer planets, it remained invisible to our telescopes. Only when it crossed inside Jupiter's orbit in late summer of 2024 did it brighten enough for Atlas to spot it. This is the challenge with detecting interstellar objects. They're typically small, dark, and only become noticeable when they're close enough and active enough to reflect sufficient sunlight or develop a visible coma. After discovery in September 2024, astronomers had a narrow window to study 3I/ATLAS intensively. The object reached perihelion, its closest approach to the Sun, in late 2024 or early 2025, passing at a distance roughly between the orbits of Mars and Earth. This was the critical period for observations, when the object would be at its brightest and most active. During this time, observatories around the world coordinated their efforts. Ground-based telescopes tracked it nightly when weather permitted. Space telescopes like Hubble and the James Webb Space Telescope scheduled precious observation time to capture high-resolution images and spectra. Radio telescopes listened for any unusual emissions. The goal was to gather as much data as possible before 3I/ATLAS faded from view. Because, make no mistake, this opportunity was fleeting. After perihelion, 3I/ATLAS began its outbound journey, heading back toward the outer solar system and eventually to interstellar space. Its velocity carried it quickly away from the Sun, and as it receded, it grew fainter and fainter in our telescopes. By mid-2025, the object would be crossing back through the outer solar system, too faint for all but the most powerful telescopes to track. By 2026 or 2027, it would pass beyond the orbit of Neptune, essentially becoming undetectable with current technology. And then 3I/ATLAS returns to the darkness between the stars, resuming its lonely voyage through the galaxy. It will travel for thousands or millions of years before potentially encountering another star system. Perhaps, in some unimaginably distant future, it will be detected by astronomers orbiting another sun, and they'll wonder, as we do, where this wanderer came from and what stories it could tell. Comparing to other interstellar visitors. 3. I/ATLAS isn't the first interstellar object we've detected, but it's helping us understand what might be typical or unusual about these cosmic wanderers. Let's compare it to the two previous confirmed interstellar visitors. First, there's one I/Oumuamua, discovered in October 2017. Oumuamua is perhaps one of the strangest objects ever detected by astronomy. It was extremely elongated, roughly cigar-shaped with a length-to-width ratio of about 10:1. It showed no visible coma or outgassing, suggesting it was more asteroid-like than comet-like. Yet mysteriously, it exhibited a slight acceleration away from the Sun that couldn't be explained by gravity alone, hinting at some form of outgassing too diffuse to observe directly. Oumuamua sparked intense speculation and debate. Some suggested it could be an artificial object, though the scientific consensus remains that it's natural. Its unusual characteristics might be explained by exotic compositions, perhaps nitrogen ice, which would sublimate without forming a visible coma. Whatever it was, Oumuamua was discovered on its way out of the solar system, giving us only weeks to study it before it vanished. Then came 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. Unlike Oumuamua, Borisov was immediately recognizable as a comet, complete with a bright coma and tail. In many ways, it resembled comets from our own solar system, suggesting that cometary processes might be universal. Borisov was also discovered earlier in its pass through the inner solar system, giving astronomers months to study it intensively. It became one of the most observed objects of 2019 to 2020. Spectroscopic analysis of Borisov revealed gas ratios, particularly the carbon monoxide to water ratio, that were unusually high compared to solar system comets. This hinted at formation in a particularly cold environment, perhaps in the outer regions of its birth star's planetary system. Now we have 3I/ATLAS, and it seems to share more in common with Borisov than with Oumuamua. Like Borisov, 3I/ATLAS displays obvious cometary activity with a visible coma. Its composition appears broadly similar to solar system comets, though detailed comparisons are still ongoing. What's emerging from these three objects is a fascinating picture. Interstellar space might be filled with debris ejected from planetary systems, both asteroid-like objects and icy comets. Statistical models suggest that billions of such objects might be passing through our solar system at any given time, but most are too small or too far away to detect. The fact that 2 of our 3 confirmed interstellar objects are comets might not be coincidental. Comets, with their volatile-rich compositions, brighten as they approach stars, making them easier to spot. Interstellar asteroids might be far more common, but simply harder to detect because they don't develop visible comas. Each interstellar visitor teaches us something new. Oumuamua showed us that strange, possibly exotic compositions exist. Borisov demonstrated that some interstellar comets are similar to our own. And 3I/ATLAS is now adding its own chapter to this story, helping us understand the diversity and commonality of objects wandering between the stars, what it tells us about exoplanetary systems. The detection and study of objects like 3I/ATLAS open an entirely new window into understanding planetary systems beyond our own. These interstellar wanderers are essentially samples from other solar systems, material we could never reach through conventional space missions, delivered right to our doorstep. Think about the implications. When we study 3I/ATLAS's composition, we're analyzing material that formed around another star, possibly billions of years ago. The chemical makeup of this comet reflects the conditions in its birth stellar nebula, the elements available, the temperature gradients, the types of ices that could condense at various distances from its parent star. The presence of familiar compounds like water, carbon monoxide, and organic molecules suggests that the basic chemistry of planet and comet formation might be similar across different stellar systems, at least in our galactic neighborhood. Stars form from collapsing clouds of gas and dust with broadly similar compositions, mostly hydrogen and helium, with traces of heavier elements. The same physical processes that built our solar system likely operate elsewhere, but the subtle differences matter too. If 3I/ATLAS shows unusual isotopic ratios, say different proportions of deuterium to regular hydrogen, or unusual ratios of carbon isotopes, that could tell us about the nuclear processes in its birth star or the specific conditions of its formation region. The very existence of interstellar objects also tells us about planetary system dynamics. How did 3I/ATLAS get ejected from its home system? The most likely scenario involves gravitational interactions during the early chaotic phases of planetary system formation. When planets are forming, many more planetary embryos exist than will survive to become mature planets. These protoplanets gravitationally scatter each other, with some being thrown into the star, others settling into stable orbits, and still others being ejected entirely into interstellar space. Jupiter and Saturn likely ejected countless comets and asteroids from our solar system during their formation and migration. So 3I/ATLAS might be a refugee from a violent planetary childhood, cast out during the formation of its home system's version of Jupiter. This means every interstellar object is potentially evidence of giant planet formation around other stars. The trajectory and velocity of 3I/ATLAS also encode information. By studying its path through the galaxy and comparing it to the motions of nearby stars, we might eventually narrow down which stellar system it came from, though this remains extremely challenging given the long timescales involved. Furthermore, the detection rate of interstellar objects helps us estimate how common planetary systems are and how efficiently they eject material. The more interstellar objects we find, the better we can constrain models of planetary system formation and evolution across the galaxy. The future of interstellar object detection. We've detected 3 interstellar objects so far, but that's just the beginning. The future of interstellar object astronomy is about to explode, and it's worth understanding why and what it means. The primary bottleneck in detecting interstellar objects is simple. They're faint and fast-moving. By the time they're close enough to our Sun to brighten significantly, they're often already on their way out. We need better surveys, telescopes that scan larger portions of the sky more frequently, with sufficient sensitivity to detect these cosmic visitors earlier. Enter the Vera C. Rubin Observatory, currently under construction in Chile. When it becomes operational, this groundbreaking facility will revolutionize asteroid and comet detection. The Rubin Observatory will photograph the entire visible sky every few nights, creating a constantly updated map of everything that moves. Astronomers estimate that once the Rubin Observatory is fully operational, we might detect 1 interstellar object per year, or possibly even more frequently. Think about that. What took us from 2017 to 2024 to find 3 examples could become an annual occurrence. This will transform interstellar objects from rare curiosities into a new class of regularly studied astronomical phenomena. With more examples, we'll be able to do statistics, understand the size distribution, composition variations, typical trajectories, and ultimately piece together a comprehensive picture of the material wandering between stars. There are also proposals for dedicated missions. Imagine a spacecraft specifically designed to intercept and study interstellar objects up close. Such a mission would need to be on standby, ready to launch within days or weeks of a detection. with sufficient fuel and velocity to match course with a fast-moving target. It's technologically challenging, but not impossible. The European Space Agency has studied concepts like the Comet Interceptor mission, designed to reach a pristine comet, potentially including an interstellar one, if detected with enough advance notice. These missions would carry instruments to analyze surface composition, measure magnetic fields, sample the coma, and capture high-resolution images of these alien worlds. There's even speculation about more ambitious possibilities. What if we detected an interstellar object early enough and on a favorable trajectory? Could we send a fast probe to place instruments on its surface, turning it into a scientific platform that we could ride through interstellar space? The technological challenges are immense. The delta V required to match speeds with an interstellar object is enormous, but not necessarily insurmountable. As our detection capabilities improve and we get earlier warnings, such missions transition from science fiction to actual engineering proposals. Beyond dedicated missions, improvements in telescope technology will help. Space-based infrared telescopes can detect the heat signature of interstellar objects, potentially spotting them earlier when they're still in the outer solar system. Larger ground-based telescopes with adaptive optics can study fainter objects in greater detail. And let's not forget artificial intelligence and machine learning. Training algorithms to automatically identify the telltale signatures of interstellar trajectories in massive survey datasets could help us spot these objects faster and more reliably. Conclusion. So where does that leave us with 3I/ATLAS? This remarkable object, a visitor from another world, has given us a precious glimpse beyond our solar system. It's a messenger carrying information about conditions around other stars, about the universality of comet formation, about planetary system dynamics playing out across the galaxy. We've learned that interstellar comets can resemble our own solar system comets in many ways. Same basic composition, same physical behavior when heated by a star. But we've also found subtle differences that hint at the diversity of environments where these objects form. 3I/ATLAS has validated our detection methods and confirmed that our improved survey capabilities are starting to reveal the population of interstellar objects that has always been passing through our cosmic neighborhood, unseen and unnoticed. As this particular visitor fades back into the darkness, already beyond our ability to observe it, we're left with terabytes of data to analyze, questions to answer, and mysteries to solve. Where exactly did it come from? What subtle compositional differences might reveal themselves in detailed analysis? What can its structure tell us about its history? But more than that, 3I/ATLAS has prepared us for what's coming. The era of regular interstellar object detection is dawning. Within a few years, these cosmic wanderers will shift from exceptional events to expected occurrences. Each new detection will add to our understanding, building a statistical picture of the material between stars. We're living through the opening chapter of a new field of astronomy. Our descendants will look back on this era, the detection of Oumuamua, Borisov, and ATLAS, as the pioneering discoveries that launched the study of interstellar objects as a mature scientific discipline. And somewhere out there, right now, another piece of another world is silently approaching our solar system, invisible in the darkness, waiting to be discovered. When it arrives, we'll be watching, ready to learn its secrets and add another chapter to humanity's growing understanding of the vast cosmic ocean that surrounds us. 3I/ATLAS came from another world, and in studying it, we've taken one more step toward understanding the billions of worlds that fill our galaxy. Thank you for watching.